Hi guys, welcome to today's session of design and analysis of algorithms. In today's session, we are going to discuss about asymptotic notations and basic efficiency classes. We are going to discuss about three types of notations: big O notation, omega notation, and theta notation. First of all, what are the asymptotic notations? What is the importance of these asymptotic notations? Asymptotic notations are used in computer science and mathematics to describe the behavior of a function as the input size grows infinitely large. So if the input size is increasing to infinite, how a function behaves, how the growth of rate in the execution of that function is present, that is to be provided by the asymptotic notations. These provide a way to analyze the performance of algorithms and data structures in terms of their efficiency and scalability. So why asymptotic notations are important? These asymptotic notations gives the simple characteristics of an algorithm's efficiency, how efficiently algorithm works for smaller input data and for larger input data. The characteristics of efficiency can be given by these asymptotic notations. And these notations allow us to compare the performances of various algorithms which are used for the same problem. And before going to know about the different types of asymptotic notations, first we need to know what the various practical complexities that are available. So in general, the time and space complexities can be represented as a function in n. And the order of functions can be represented in the form of a hierarchy that describes the growth rate of various functions as the input size n increases. Here you can see the order of growth of the different functions. Here, this becomes one function, this becomes another function, this becomes another function. How the order of growth is there? So for the smaller inputs, the order is, it is having one order. For the next input, it is having log n. For the next, as the size grows, next it gives root n. As the size grows, it gives n. As the size grows, it gives n log n. Like that, n square, n cube, 2 power n, 3 power n, and so on, n power n. Like this, the complexities can be represented. So this is the maximum complexity, and this is the minimum time complexity. Suppose, for example, we are given a function f of n is equal to n. Now, what becomes the upper boundary for this time complexity? For n, the upper boundary classes are n log n square, n cube, so on, up to n power n. What are the lower boundary representations for this n? 1 log n root n. These are the lower boundary representations. Right. Now, for the representation of these upper bounds and the lower bounds of time complexities, we can use these asymptotic notations. So what are the major asymptotic notations? The commonly used asymptotic notations in our computer science are big O notation, omega notation, theta notation. Here you can see the symbols what we use for the representation of these notations. Big O, this is omega, and this is theta notation. Now we will see about each and every type of notation, how it mathematically represented, how it graphically represented, and what is the example for that representation. Coming to big O notation, big O notation is a commonly used mathematical notation to describe the upper bound of rate of growth of a function. It always represents the upper bound for time complexity. Now, how mathematically this can be defined? A function f of n is equal to big O of g of n. Here, we need to read it as f of n is equal to big O of g of n. If and only if there exist two positive constants c and n naught such that f of n less than or equal to c into g of n. Definitely the function should have a less value when compared to that of g of n. Since we are calling it as f of n is equal to big O of g of n, and this represents the upper bound. Since it is representing upper bound, the g of n is to be called as upper boundary value for the function f of n when it is satisfying this inequality f of n less than or equal to c into g of n for all values of n where n greater than or equal to n naught. Now mathematically it can be represented as f of n is equal to big O of g of n implies and implied by there exists c such that f of n less than or equal to c into g of n for all n greater than or equal to n naught. So if the two functions f of n and g of n are satisfying this inequality for some value of c and for the value of n naught, we can say that the function f of n is equal to big O of g of n. How this graphically represented? Here you can see a graph. Here we represented n value in the x-axis. Here you have f of n. Here you have c into g of n. Whatever it may be the values of f of n and c into g of n before some value n naught. After that value n naught, always the c into g of n represents a larger value. C into g of n represents a larger value. That is, this g of n is upper boundary for this function f of n. So here you can see an example. F of n is given as 4n plus 3 and g of n is given as n. Now, for which values of c and n naught, the function g of n is to be called as upper boundary for the function f of n. Now, when I can say the function f of n is equal to big O of g of n, when the inequality f of n less than or equal to c into g of n is satisfied. So here you can see we are taking n naught is equal to 3 and c is equal to 5 we are taking. Let us see why we need to take c as 5. Here you can see the function f of n already contains a multiple of 4 for n. And in addition to that multiple of 4, it is added with 3. Definitely, the g of n should be greater when it is taken as c 5. That's why we have taken it as 5. Even we taken c as 5, for n value 1, this inequality cannot be satisfied. Let us see, 4 into 1 plus 3. What it becomes? 7 less than or equal to 5 into 1. 7 is not less than or equal to 5. So that's why for n is equal to 1, it is not satisfying. For n is equal to 2 also it is not satisfying. But from n is equal to 3 onwards, this inequality is satisfied. So we can say that 4n plus 3 is equal to big O of n implies and implied by there exist 5 such that 4n plus 3 is less than or equal to 5 into n for all values of n where n greater than or equal to 3. So like that, for which values of c and n naught, these two functions f of n and g of n are satisfying the big O notation that can be represented. Coming to the next one, omega notation. Omega notation is a mathematical notation used to describe the asymptotic lower bound or best case scenario of a given function. Now, how to define this omega notation? Let us see here. The function f of n is equal to omega of g of n if and only if there exist the positive constants c and n naught such that f of n greater than or equal to c into g of n for all the values of n where n is greater than or equal to n naught. So here, since this represents the lower bound, the inequality should be f of n greater than or equal to g of n. Right. Now here, mathematically, this can be represented as like this. f of n is equal to omega of g of n implies and implied by there exists c such that f of n greater than or equal to c into g of n for all n where n greater than or equal to n naught. How mathematically omega notation can be represented? Here you can see a graph how mathematically the omega notation can be represented. Here n values are represented on x-axis. Whatever it may be the values of f of n and c into g of n before n naught. Sometimes f of n may be greater, sometimes g of n may be greater. But after n naught, after some value of n, that is n naught, after n naught, always f of n gives the upper value and c into g of n gives the lower value. That's why we are saying that this omega notation gives the lower bound. Here you can see an example. Here f of n is given as 8n square minus 3 and g of n is given as n square. So here when n naught is equal to 2, here we are taking n naught value as 2 and c value as 7. Definitely c value should be here. We are subtracting the value from 8n square. Since we are subtracting this value, definitely the value of n naught, the value of c should be less than 8. So here we have taken 7. If you take 6, the n naught value will be changed. If you take 5, n naught value will be changed. Here I have taken 7. For this 7, the n naught value becomes 2. Right? From 2 onwards, for all values of n, this inequality is folded. So that's why we can say that the function n square becomes lower boundary for this function 8n square minus 3. Right. Coming to the theta notation. Theta notation is a formal method of expressing both upper and lower bounds. Our big O notation is used to represent upper bound. Omega notation is used to represent lower bound. Whereas the theta notation is used to represent both upper and lower bounds. Now here you can see the mathematical representation for theta notation. F of n is equal to theta of g of n if and only if there exist two positive constants c1, c2 and also n naught such that c1 into g of n less than or equal to f of n less than or equal to c2 into g of n. Here it is representing lower bound and here it is representing upper bound for all values of n greater than or equal to n naught. Here this notation gives the mathematical representation for that particular definition, and the graphical representation for theta notation is like this. So whatever it may be the values of f of n, c1 into g of n and c2 into g of n before this n naught, from n naught onwards, always c2 into g of n gives upper value for f of n and c1 into g of n gives lower value for f of n. And here you can see an example. F of n is equal to 3n plus 2 and g of n is equal to n. For the values of c1 and c2, here we are taking the values of c1 and c2 as 3 and 4. For the values of 3 and 4 of c1 and c2, for the values n naught is equal to 2, the two inequalities are folds. So that's why we can express the function 3n plus 2 is equal to theta of n, which gives both upper and lower boundaries. So I hope that you all understood all these three asymptotic notations: omega notation, big O notation, omega notation, and theta notation. So in our next session, we are going to see about recursive algorithms. Thank you for listening this session.